All right, we're going to solve this differential equation that shows up in all sorts of situations where the rate of change of some quantity is proportional to that quantity. And we're going to solve this by separating the variables. dy over y equals k dt. And then we'll integrate both sides. The integral of 1 over y is the natural log of the absolute value of y, and the integral of a constant with respect to t is just that constant times t, and we have our constant of integration. All right, now we want to solve for y. Let's solve first for the absolute value of y. So to undo the natural log, we want to use e as a base on both sides, so e to the kt plus a c, and if the absolute value of y is equal to that, then y itself must be equal to either plus or minus that. All right, so now we've got it solved for y. We can make it a little bit nicer looking if we notice by exponent rules that expression right there could be written as e to the kt times e to the c. I realize that's not much nicer yet, but e to the c can be any positive number at all, and combined with that represents any positive or negative number, so that is actually just another constant. So our general solution to this differential equation is y equals some constant times e to the kt. Let's actually go a step further and think about the situation where we might know how much of y there was when time was 0. So let's call y of 0 y naught. And in that case, our solution, we can find the a for our solution. We can say y naught would be equal to a e to the k times 0. E to the k times 0 is just 1. So y naught is a, which means that the solution to this differential equation, y, is just equal to however much of y there was at time 0 times e to the kt. Now this equation should look very familiar to you. It's the equation for exponential growth, and so it shows up, for example, you saw it when you did interest with continuous compounding, because your money, when you're earning interest, grows at a rate proportional to how much you've got in the bank. So that k in that situation is the r in the continuous compounding model. And therefore, the amount of money you put in the bank was that y0, and the amount of money you have after time t comes up to be y.